by solving one problem only. And today I will try to some other problems, almost similar problems. Okay. So yesterday I solved this type of problem. There were two shafts. One was a solid shaft, another one was a hollow shaft, and the applied torque was known, and we were asked to determine the stresses at three locations: at here, at here, at here. Okay, and we solved it in the last class, and today I will try to solve some other problems. So we can start example number. It is an example. Basically, I am following for this course, for this topics, I am following mechanics of materials by Hibler. Okay, I told it in the class already. So the book's name is Mechanics of Material, title, and the writer is Hibler. So it is an example. So this figure shows it is showing that actually it is a support, fixed support. Okay, and it is a tube, or it is a pipe, and this pipe is tightening to the support. This pipe is tightening to the support by a wrench, and this one is known as wrench. I think all of you have all of you are familiar to this type of wrench. You will see it in the garage, in drilling, in soil boring, or in carpenter work. Okay, you will see this type of wrench. Okay, and so this pipe is tightening to this support using this torque wrench. Okay, and by hand. This one is left hand, this one is right hand. So torque is applied by these two hands. By left hand, 80 Newton force is applied upward, and by right hand, 80 Newton force is applied downward. And the locations of the hands are: for left hand it is 200 millimeter leftward from the tube pipe, and right hand is 300 meter rightward from the pipe. Okay, determine the shear stress developed in the material at the inner and outer wall along the central portion of the pipe. We have to determine the stress developed due to this applied torque at the inner surface and outer surface of the pipe. The inner radius of the pipe is 40 MPa, and the outer radius of the pipe is 50 MPa. Okay, 40 MPa and 50 MPa. So we know the torsional formula equals to tau equals to T rho by Z. T rho by Z, torsional formula. Say, look at here. It is the torsional formula. T rho, for this problem, for maximum case, it will be the remote location. So for general case, it is T rho by Z. T is the developed torque. T is the developed torque, and rho is the distance of the location from the origin, and Z is the sectional properties, polar moment of inertia. So to determine the stress, we have to know the developed torque, the location of the distance of the location from the origin, and the sectional properties. Okay, so the sectional property, when we will know the inner diameter and outer diameter of the pipe, then we can determine the polar moment of inertia easily. So we can determine the value of Z, and we have to determine the stress developed at the inner surface. So its location is 40 millimeter from the center, and also the stress at the outer surface. So its location is 50 millimeter from the center. So rho is known, and so rho and J are known. So we have to know the torque. Okay, we have to know the developed torque at the location. So along the length of the pipe at each location, the torque will be constant, because torque is applied here. Torque is applied at the free end. So along the length from the free end to the support, the developed torque will be constant. Developed torque will be constant as the torque is constant, and the size of the pipe is constant, uniform. So the stress at inner surface at any location will be same. Similarly, the stress at the outer surface will be similar at each point. So first of all, we have to determine the applied developed torque. So as it is not clearly mentioned that that pipe is subjected to torque, but using the properties of the applied torque, we have seen that the pipe is subjected to a torque. Okay, will be subjected to a torque according to the properties of the applied torque, because properties are: one force is applied upward, which is 80 Newton, another force is applied downward, 80 Newton, and both forces are parallel to each other, and one force is upward, another force is downward. So these two forces will create torque. Understand? So these two forces will create torque. So as it is not mentioned that this pipe will be subjected to a torque, but according to the properties of the applied force, it is clearly it is clear that this pipe is subjected to a resultant torque. So the torque is what is the value of torque? Applied torque. Torque is force times the distance between the forces. So force is 80, and distance between the forces, distance is 200 plus 300. That means 500 millimeters. So to convert into meter, it will be 0.5 meter. So the applied force torque will be 80 times 0.5, and it is the developed torque according to the principles of equilibrium. According to the principles of equilibrium, applied force will be equal to developed force. Otherwise, there will be otherwise the structure will be unequilibrium or imbalance. So according to the equilibrium condition, applied force will be equals to the developed force. So this is the applied torque. So developed torque or internal torque will be this one, 40 Newton. So developed torque is known, and this is the polar moment of inertia, as it is a hollow section. So we know for hollow circular shape, the polar moment of inertia is pi by 2 C naught. C naught means the outer radius to the power 4 minus Ci, that means inner radius to the power 4. So this is the sectional properties, and use the general equation of polar moment of stress, shear stress. Okay, shear stress. So it is Q rho by J. Q is known, and it is applied developed torque, which is 40, and J is known, which is this one. And to determine the stress at outer point, we have to use the distance of the outer point from the origin, which is nothing but 0.05. So it is the shear stress developed at the outer surface. And similarly, if we substitute the value of inner radius, then we will get the stress at the developed at the inner surface. Okay, so this is the stress at the outer surface, it is the stress at the inner surface. And now if we want to show the stress in a block diagram, then we will take a block from here and we will take another block from here. And if we take a block from here, so first of all we have to determine the direction of the stress, shear stress. it is the cross section, so shear stress will be either this way or either that way. And look at this figure. The developed torque is anti-clockwise for this section. Developed torque is anti-clockwise for this section, and go to the previous one. If we consider this segment, the developed torque will be anti-clockwise. So for this section, developed torque will be clockwise. Is that clear? For this section, developed torque is anti-clockwise. So for that section, that means for section A to C, the developed torque will be clockwise. That's why it is clockwise torque. Okay. So actually, this torque is nothing but the torque developed by the shear stress at different locations. Okay, at different locations. So the direction of the shear stress will be such that the torque developed by the shear stress, the direction of the torque developed by the shear stress will be similar to the direction of the developed torque. So direction of the developed torque is clockwise. So direction of the torque developed by this stress will be clockwise. So definitely the direction of the stress will be along this line. Okay. So if we consider this block, come to this block. So the direction of the shear stress is this one. Okay. Direction of the shear stress is this one, and imagine there is no stress. Excuse me. Okay, wait, please. I am not recording. I have to record the. Is it recording? Okay, thank you. Okay, so imagine there is no stress. Then what will be happen? This block will spin this way, right? This block will spin this way. So, but according to equilibrium condition, this block will not spin. So definitely there will be another shear stress, and another shear stress, and direction will be this direction. So that this stress will create anti-clockwise spin, and this stress will create clockwise spin. So anti-clockwise spin and clockwise spin, one spin will be counterbalanced by another spin. Okay, and similarly, come to this point, come to this block. So this is the stress developed by the due to the torque. So this is the stress, and as it is upward, so it will try to spin the block this way. So this so there will be another shear stress that will try to create the anti-clockwise spin. Okay, so this is the stress block at this location, inner surface, and this is the stress block at outer surface. And then what are the application of torque? Actually, torque is applied in mechanical engineering most of the time. In civil engineering problem, its application is very limited. Actually, torque will be created, or torque will be generated by any motor, and that torque will be transmitted to other shaft to generate or to work some to do some work. Okay, and that is known as power transmission. Power transmission. So if say it is a wheel, and this wheel is subjected to an applied torque T. Okay, applied torque T, and this torque has been displaced by d phi angular distance. Excuse me. This applied torque has been displaced by this amount of angular displacement within time dt. Within time dt. So how much work has been will be done? How much work will be done if this torque is displaced by this amount within this time? We know work equals to force into distance, force into displacement, or force into distance. So if we consider linear force, then we will use linear displacement. If we consider angular force, then we will use angular displacement. But same thing. In general, work equals to force into displacement. If we consider linear force, that means axial tension or axial compression, then we will use axial contraction or axial extension. That means the linear displacement. But if we consider the angular force, torque is nothing but a force. In general, torque is force. Torque is a force. Bending moment is also a force. Okay. So for angular force, displacement will be angular displacement. So as the torque is angular force, so it is also an angular displacement. So when this torque is displaced by this displacement, work will be force time displacement. So force time displacement, that is the total work. And this amount of work has been done within time dt. And so what is the work done by per unit time? Work done by per unit time. So work done, it is the total work done, and this work done has been done by this time. So work done by one unit time will be this. Okay, so this is the angular displacement, that is the angular that is the time. So this angular displacement has been occurred within time dt, so it is nothing but angular velocity. Okay, it is nothing but an angular velocity. And if f is the frequency of the shaft's rotation, frequency means the complete cycle per unit time. Complete cycle per unit time. So if f is the frequency, that means f number of complete cycle is completed by unit time. That means either 1 minute or either 1 second, either 1 hour. Okay, so how much angular displacement has been completed by 1 second or 1 minute? It will, for one complete revolution on complete cycle, the angular displacement is 2 pi. So f number of cycle, total angular displacement is 2 pi f. So that is the total angular displacement per unit time. So it is nothing but angular velocity. So this is the expression of power in terms of angular velocity, and this is the expression of power in terms of frequency. Okay, and then shaft design. So basically, what do you mean by design? Design in engineering problem and in architectural problem, the definition of design is slightly different, completely different, not slightly, completely different. In architectural design, architectural point of view, design means the shape. Okay, design means the shape and size of the structure. That is the design. But in civil engineering problem, design means the what will be the size? What will be the size of the section? That is the design. So if you are asked to design a column, that means you have to determine the length and breadth and width of the column section. Or if you are asked to determine the design a beam, that means you have to determine what will be the width of the beam and what will be the depth of the beam to carry the applied force. That is the design. So in this case, shaft design means we have to determine the size of the shaft so that the applied force can carry the shaft easily or can resist the shaft easily, and this can be done using this. It is nothing but the general expression of shear stress in terms of applied torque. Okay, applied torque. Okay, and in case of design, so if you are asked to design a column, in that case you will determine the size of the column so that due to the applied force, the stress developed in the column will not exceed the strength of the material. That means capacity of the material. Okay, capacity of the material. That means for designing purpose, we will consider always the capacity of the material. Capacity of the material, that is known as most of the time allowable stress. So we will consider the allowable stress, and allowable stress is nothing but a maximum stress. Okay, so for the maximum stress will be developed at the remote location or the outer surface. That's why here rho is replaced by C and J is constant. It depends on the shape of the cross section. So from this equation, if we know the applied torque, if we know the allowable stress or the strength of the material, then from this term we can easily determine the size of the shaft, because in J it is nothing but an expression in terms of radius of the shaft, and it is also the radius. So on the left side it is only this term contains the term C or radius. Okay, now try to solve a problem. So it is nothing. It is an example again. Actually, M is a motor. It is a motor, and it is a steel. It is a solid shaft, and this shaft is made of steel. The shaft is made of steel, and the allowable stress of the steel is 14.5 ksi. 14.5. That means if the maximum stress developed in the shaft at anywhere in the shaft exceeds this value, that means 14.5, then this shaft will be failed. Okay, this shaft will be failed. That's why it is the maximum allowable limiting value. And torque power is transmitting by the motor. Excuse me. Power is transmitting by this motor through the shaft to this wheel, or to this what is it known? It is, I have forgotten the name. Say it is wheel. Okay, and this wheel is connected to another parts of the engine by a belt. Okay, so this motor is transmitting power, and the power is 5 horsepower. 5 horsepower, and due to this 5 horsepower, this shaft, this shaft or this wheel is rotating at this with this speed, 175 rpm, revolutions per minute. That means the angular velocity of this shaft or of this wheel is 175 revolutions per minute. Then we have to determine the required diameter of the shaft. We have to determine the minimum diameter of this shaft, so that due to this power, the shaft will not be failed, and the strength of the shaft's material is 14.5 ksi, and the diameter will be nearest to 1/8 inch. Okay, so first of all, basically we have to use this equation. To use this equation, we have to know the value of developed torque. And developed torque is nothing but the applied torque, because according to equilibrium condition, developed torque, applied torque equals to developed torque. So basically in this equation it is developed torque. It is not applied torque, but numerically both torques are same, although the sign convention is different. If the applied torque is clockwise, developed torque will be anti-clockwise. So to use this equation, we have to know this term, and we have to know this term. This term is given. It is the allowable strength, which is 14.5 ksi. It is given, and we have to determine the applied torque. And we know power equals to T omega. Omega is the angular velocity, which is given 175 revolutions per minute, and power is given, which is 5 horsepower. So we have to convert it to either FPS system or MKS system. So we feet pound per second, and 175 rpm is equivalent to 18.33 radian per second. So if we substitute this and this value in this equation, then the value of torque will be 150.1 feet pound. Okay, and now come to this equation. So now this torque is known, allowable limit is known. So, and J is nothing but polar moment of inertia for solid shaft, which is pi by 2 c to the power 4. Pi by 2 c to the power 4. So by solving this equation, we will get the value of C, which is 0.429 inch. So it is the radius. So diameter will be 2c, which is 0.858 inch. But we are requested to determine the diameter nearest to the 1 by 8 inch. 1 by 8 inch. So if you convert, this value in terms of A by B, that means numerator by denominator, then you will see that numerator will be 6 point something divided by 8, 6 point something divided by 8. So we have to determine it nearest 1 by 8. So ultimately it will be 7 by 8 inch. Okay, and it is a problem. It is not an example. It is a problem. Basically, when you will learn the geotechnical engineering course, then you will see this type of problem available frequently. Actually, it is a drilling problem. It is a shaft, solid, hollow. It may be hollow or solid shaft, and at the end there will be a blade. Basically, there will be 3 blades most of the times. The blades are located at 120 degree one from each other. Okay, and this after inserting this tube and blade into the soil, and it will try to rotate. It will try to rotate to determine the shear strength of the soil. But what will be happen if you want to rotate? It is the support, or you can it is the driving unit. That means basically to rotate this assembling or this set, you have to apply torque here. And if you apply torque here, then this blade will try to rotate, and when this blade will try to rotate, then it will create shear stress, and when there will be shear stress, there will be torque. And that torque is designated by TA. That means TA is the torque developed by the blade. Okay, and again, if you try to rotate this shaft, shear stress will be developed on the surface of the tube. Okay, on the surface of the tube. Okay, and so due to the shear stress, another type of torque will be developed. And it was observed that the shear stress developed on the surface of the tube depends on the depth. It depends on the depth of soil. That means it is very small here. It is 0 here, and if you go more depth, then shear stress will be more. And the shear stress is varying linearly from top surface to the bottom surface. It is varying linearly, and it is increasing from top surface to the bottom surface. So, therefore, the developed torque due to the shear frictional stress or shear stress will be varying linearly from minimum at the surface and maximum at the bottom point. Okay, and that is at this location. This is the variation of this is the variation of developed torque resistance torque developed by the frictional force, and at this location it is TA. So it is varying linearly. Basically, it is a triangular shape, and the length of the shaft inserted into the soil is L. Then you have to determine the minimum torque TB. Minimum torque TB that must be supplied by the drive unit to overcome the resisting torque. That means if you try to rotate this assembly, then one torque will be developed here, another torque will be developed here. So you have to apply such amount of torque at here, so that this torque and that torque will be overcome. Okay, so we have to determine that amount of minimum amount of applied torque TB, and calculate the maximum shear stress in the pipe. The pipe has an outer radius R0 and the inner radius Ri. Okay, so according to equilibrium equation, condition, internal torque will be equals to external torque. That means developed torque will be equals to applied torque. So it is the concentrated torque TA. TA is the concentrated torque. It is anti-clockwise. If you assume anti-clockwise positive, so that one is positive, and these are the torque developed due to frictional force. So that is also anti-clockwise. So that will be also positive. And as it is varying linearly, so the total resultant torque due to this varying torque will be a half base height. It is a triangle, and triangular area is half base height. So half base height. So it is the total torque, total resultant torque of the varying torque, and it is a concentrated torque. So these are two developed torque. So total developed torque is that one, and this one is the applied torque. So applied torque is this, and so this is the minimum value of the applied torque. And we have to again calculate the maximum shear stress, and maximum shear stress T C by Z. T is this one, and C is the radius, and definitely maximum stress will be developed at the outer surface. So it is the outer radius, and Z is the polar moment of inertia, which is pi by 2 R0 to the power 4 R minus Ri to the power 4. So that is the expression of it. Is not actually, it is an expression. Then it is another problem, and it is also a shaft having varying section. This is support, fixed support, and at here the size is maximum, and if you go far away from the support to the free end, the size is minimum. And this shaft is subjected to a torque. This shaft is subjected to a torque, and the size of the torque, size and surrounding environments of the shaft is such that the torque will be developed. Torque will be developed along the length of the shaft, but the torque will not be uniform. It will be minimum here, it will be maximum here, and the variation of the torque is not linear. Okay, yeah, this figure shows the developed torque. It is not the applied torque. Okay, it is the developed torque. So the variation of the torque is non-linear, which is expressed at 10x square. X is the distance from this location. X is the distance from the free end. Okay, so the expression of the variable torque is 10x square. Now, if the maximum stress, if the shaft is remain to constant at 80 MPa, that means we have to apply a torque to this shaft, so that we have to apply a torque to this shaft, so that the stress along the maximum stress along the length of the shaft. That means the stress at the outer surface along the length of the shaft will remain constant, which is nothing but 80 MPa. Okay, as the torque is varying, torque is not linear, torque is not uniform, it is varying. And if you have to maintain a constant maximum stress, that means constant stress on the outer surface, therefore you have to change the size of the shaft. You have to change the size of the shaft along the length. Otherwise, the stress on the outer surface will not be constant. It will be variable. So to maintain the constant stress at the outer surface, we have to provide different section along the length. Okay, and determine the required variation of the radius C. The C is the radius of the shaft. We have to determine the variation of the C. That means we have to determine an expression of C in terms of X. In terms of X. So first of all, we have to determine how much amount of torque have to be applied to the shaft. Have to be applied to the shaft. Okay, we can determine it in the reverse way, because if we can determine how much amount of torque has been developed on the shaft, then we can determine how much amount of torque was applied to the shaft, because developed torque and applied torque are numerically same. Magnitude of both torques are same. So as the information of the applied torques are not given, but the information of the developed torque is given, the variation of that developed torque is here. So if we integrate the torque from free end to support, then we can get the total amount of developed torque. And that amount of so if we know the total amount of developed torque, so the applied torque will be similar to the total amount of developed torque. Okay, so for in that case, as the torque is varying, so we can consider, and you can consider a small element or a small segment from here. The length of the segment is dx. Length of the segment is dx, and dx is very small. And as the dx is very small, so we can assume that the dx segment is subjected to uniform torque T. That means as the dx is very small, therefore we can neglect the variation of T along the length dx, as the dx is very small. Therefore the total torque developed on the element dx is T dx, and if we integrate from 0 to x, then we can get the total torque. So the total developed torque is 10 by 3 x cube. So that is the total applied torque. Okay, that is the total applied torque, and we know stress equals to T rho by J. So if we want to determine the maximum stress, so rho will be C, and it is nothing but it is given here 80 MPa. Maximum stress will be 80 MPa. So this one is given 80 MPa. To convert into Newton per meter square, it is 10 to the power 6. And T is this one. C we have to determine, and C, J is the polar moment of inertia. It is in terms of it will be pi by 2 C to the power 4. So from by solving this equation, we can get an expression of C, that is 2.98 x. That means this equation shows the variation of size of the shaft. So this equation shows that at this point the size is 0. Okay, that means this end will be sharp. It is not similar to the given shape as given drawing. Actually, it will be 0, because this equation shows if x is 0, c is 0. That means it will be a sharp free end. And it is another problem. At the time, it is another problem. it is there is a solid shaft having uniform cross section. That means along the length the cross section is same, constant. That means the radius or diameter of the shaft is constant along the length, and this shaft is fixed at C, and it is subjected to different torsions. One concentrated torsions at free end, another concentrated torsion is applied at this location, which is 0.2 meter away from the support, and this length is subjected to uniform torsion, which is 4 kilonewton meter per meter. So it is a distributed torsion, similar to a applied force, UDL, uniformly distributed load. And this shaft is made of a material. This shaft is made of a material whose strength is 60 MPa. Material strength is 60 MPa. That means if the maximum stress developed in this shaft exceeds this limit, then this shaft will be failed. So we have to determine the diameter, required diameter. That means minimum diameter. We have to determine the minimum diameter of the shaft if the allowable stress for the material is 60 MPa. Allowable stress is 60 MPa. That means maximum stress will not exceed 60 MPa. Maximum stress will be equals to 60 MPa or less than 60 MPa. Okay, so we know the equation of shear stress. Equation of shear stress is, look at here, equation of shear stress is P rho Z. So shear stress depends on the value of torque, value of location or the distance of location from the origin, and it is constant. Z is constant for any specific section. Z is constant. It will not vary from point to point. But the value of rho varies from point to point, and T is also constant. So to determine the maximum value, rho will be C. Okay, so C is also constant for maximum case, and Z is also constant for maximum for any case. So to get the maximum value of tau, we have to determine the maximum value of torque. Because if the structure is subjected to, come to here, the structure is subjected to different types of torques at different locations. So we do not. So we cannot say that the shaft is subjected to a constant torque. At different locations, the developed torque will be different at different locations. So to determine the maximum torque at maximum stress using this equation, we have to know the maximum torque. Okay, maximum torque. So we will first. Okay, time is over, and my head is calling me, so I have to go. So I will finish it in the next class. Okay, do you have any question? If you have any question, please ask quickly. Do you have any question, please?
স্যার একটা কথা ছিল স্যার।
Sure.
স্যার আমাদের ওই যে ক্লাসের যে রেকর্ডিংটা স্যার, ওটা স্যার প্রতিদিন দিয়ে দিলে স্যার সুবিধা হতো স্যার।
হ্যাঁ, আমি রেকর্ডিং আসলে সেদিন রেকর্ড করছি, কিন্তু এইটা অটোমেটিকলি সেভ হওয়ার কথা, সেই লোকেশনটা আমি মানে যেখানে সেভ হওয়ার কথা সেইখানে ওইটা আমি পাচ্ছি। তো আমি এইটা পেলে আমি তোমাদেরকে করে দেবো, রেকর্ডিংটা দিয়ে দেবো, এবং আমি যে স্লাইডগুলো পড়াচ্ছি তোমাদেরকে, ওই স্লাইডগুলোর পিডিএফ কপি সবাই এখানে দিয়ে দেবো। ঠিক আছে, ওরি দেওয়ার কিছু নেই, আমি স্লাইডগুলোর পিডিএফ কপি এখনই দিচ্ছি না, কেন একটা টপিক শেষ হওয়ার পরে তারপরে ইয়েটা দিয়ে দেবো, এক একটা স্লাইড মানে টোটাল স্লাইডটা দিয়ে দেবো, মানে টপিকস ওয়াইজ দেবো। আদারওয়াইজ হবে কি, একটু এখন দিলে একটু পরে দিলে তোমরাও হারাই ফেলবে, আমার জন্য এটা কষ্ট হবে। ঠিক আছে, আর তোমাদের ইয়ার জন্য আমি বলতেছি, এটা আপ টু দ্য রেকর্ড, তোমাদের কিন্তু অ্যাটেন্ডেন্স অটোমেটিকলি সেভ হয়ে যাচ্ছে। তো তোমরা কতটুকু গুগল ক্লাস সম্পর্কে কতটুকু জানো আমি জানি না। তোমরা কে কখন ঢুকছো কে কখন বেরোচ্ছো দিয়া এটা কিন্তু অটোমেটিকলি সেভ হয়ে যাচ্ছে এবং ওখান থেকেই কিন্তু আমরা অ্যাটেন্ডেন্স কাউন্ট করবো। ঠিক আছে, তো তোমরা সেইভাবে করবা যে কখন ঢুকবা কখন বের হবা। অনেকে হয়তো চিন্তা করো যে ঢুকেই বের হয়ে যায়, স্যার তো আর দেখতেছি না, সমস্যা নাই। তো এটা কিন্তু আসলে রেকর্ড হয়ে যাচ্ছে যে কে কখন ঢুকছে কে কখন বের হচ্ছে, ওখান থেকে কিন্তু আমরা অ্যাটেন্ডেন্স কাউন্ট করবো। সো বি কেয়ারফুল অ্যাবাউট দ্য অ্যাটেন্ডেন্স। ওকে, এনি আদার কোশ্চেন?
স্যার একটা প্রশ্ন
স্যার আমি
বলো।
স্যার আমাদের টর্শনের আগ পর্যন্ত তো বোধহয় স্যার আমাদের সিঙ্গারের বই ফলো করা হয়েছিল। তো
হ্যাঁ,
টর্শন মানে কোন বই?
এটাও আসলে সিঙ্গারের, আমি সিঙ্গারের বইটা বেসিক্যালি ফলো করতাম, কিন্তু সিঙ্গারের বই এগুলো তো সব 3D ডায়াগ্রাম, এগুলা তোমার যদি ওই ফটোকপি করে করা হয় তাহলে ওটা ক্লিয়ার দেখা যায় না। আর এই বইটা আমি তোমাদের আগেই বলছিলাম, এটা আমি কানাডাতে যখন কোর্স করেছি তখন বইটা আমি নিয়ে আসছিলাম, সেগুলোর জন্য দেখো ছবিগুলো কিন্তু কালারফুল, যে কারণে তোমাদের কাছে এটা ক্লিয়ারলি ভিজিবল হয়। তো এটা এই বইটা আর ওই বইটা বেসিক্যালি সেম থিং, ওটা একটু তোমার একটু ব্রিফ করে লেখা আর এটা একটু এলাবোরেট করে লেখা, এইটাই। এটা আসলে আমি এই অনলাইন ক্লাসের জন্যই আমি এটা ইউজ করতেছি, আদারওয়াইজ আমি ওইটাকে ইউজ করি।
স্যার আমরা তাহলে মানে টর্শনের ক্ষেত্রে ম্যাথ প্র্যাকটিসের জন্য সিঙ্গারের বই ইউজ করব?
যে কোনোটা করো, একই জিনিস, মানে একই ফর্মুলা, ওটাও ইউজ হবে একই ফর্মুলা, এটাও একই ফর্মুলা। হয়তো ফিগারগুলো একটু ডিফারেন্ট, ওটা ফিগারগুলো ম্যাক্সিমাম ফিগারই হচ্ছে 2D আর এটা সব ফিগারই হচ্ছে 3D।
আপনি মানে ক্লাসে সিঙ্গারের বই ফলো করতে বলছিলেন তো, বিশেষ করে ম্যাথের জন্য, সেজন্য।
হ্যাঁ, সিঙ্গারের বই ফলো করো, সমস্যা নেই। ওখানে অনেকগুলো एग्जांपल দেওয়া, এক্সারসাইজ দেওয়া আছে, एग्जांपलও করা আছে। তোমরা দুইটা বই একটু কম্পেয়ার করে দেখতে পারো, এক সেম থিং, আসলে কিছু ডিফারেন্ট না।
জি স্যার, থ্যাংক ইউ।
ওকে, এনি কোশ্চেন? আমাকে আসলে হেড রাখতেছ তো, একটু তাড়াতাড়ি যেতে হবে।
স্যার আসসালামু আলাইকুম।
ওয়ালাইকুম আসসালাম। তো হ্যাঁ বলো।
স্যার আমি 17 পেয়েছি।
আচ্ছা বলো।
স্যার আমি 17 পেয়েছি।
হ্যাঁ
গুগল ক্লাসরুমে অ্যাড নাই স্যার। স্যার যদি অ্যাড করে দিতেন একটু।
তুমি তো এইটা অ্যাড হইছো আপনি?
জি স্যার, কিন্তু আমি গুগল ক্লাসরুমে আমি অ্যাড নাই।
এইটাই তো গুগল ক্লাসরুম, গুগল ক্লাসমেট, মানে অসুবিধা নেই। এখান থেকে ওই যে তোমার তো বেসিক্যালি অ্যাটেন্ডেন্স নিয়ে চিন্তা, এটা এখান থেকে হয়ে যাচ্ছে, সেভ হয়ে যাচ্ছে। মানে গুগল ক্লাসরুমে কিছুই না, গুগল ক্লাসরুমে ক্লাস নেওয়া যায় না, তো ওইখানে আরেকটা অংশ হচ্ছে গুগল মিটের মাধ্যমে লেকচার দেওয়া হয়, আর ক্লাসরুমের মাধ্যমে পরীক্ষা নেওয়া যায় বা তোমার অ্যাসাইনমেন্ট দেওয়া যায়, এগুলো।
জি স্যার, ওই কারণে স্যার পিডিএফ এগুলানোর জন্য।
হ্যাঁ, পিডিএফটা আমি এখানে ইসে দিয়ে দেবো, তোমার মানে হোম পেজে দিয়ে দেবো, যাতে ওখান থেকে সবাই নিয়ে নিতে পারবে।
স্যার মানে স্যার উনি বলতে যাচ্ছিলেন ওনাকে যদি ইনভাইট করা হতো তাহলে স্যার ভালো হতো গুগল ক্লাসরুম।
ওকে, তো তোমাকে তো ইনভাইট করা হয়েছে, তোমার এটা বলো তো একটু।
স্যার আমি বলে দিচ্ছি স্যার।
হ্যাঁ বলো।
স্যার U1701
17 না, ওই নামটা বলো।
স্যার তাহাজুল ইসলাম পিয়াস।
তাহাজুল, তাই তো? তাজরিন, হ্যাঁ তাহাজুল আহমেদ।
না স্যার, তাহাজুল ইসলাম।
আচ্ছা, তাহলে তো তোমাকে দেখা যাচ্ছে। আচ্ছা, তোমার ইয়েটা বলো, আমি তাহলে তোমাকে ইনভাইট করে দিই। তুমি তো ইনভাইট পাওয়ার কথা আই থিঙ্ক। তারপর তুমি ইয়েটা বলো, তোমার ইয়েটা আইডিটা বলো তো।
স্যার U1701091
U1701, হ্যাঁ
091 @ student.sued.
আচ্ছা, তোমার হচ্ছে U1701091 @student.
.sued.
আচ্ছা,
.ac.bd.
.sued.ac.bd। পেয়েছি তোমাকে। আচ্ছা, তোমাকে তাহলে ইনভাইটেশন পাঠিয়ে